Hello, everyone. Good day, good morning, good afternoon, wherever you may be here on Moon. It's exciting to be. We're going to talk about one of our projects that's situated on the Moon. And we is Georgi, Petrov, and myself, Christoph, Timm.
Good day.
And let's get going.
So I'd like to first take a look at the really big picture and step out. This is a picture that inspired me when I was a young kid. And it was an idea that Carl Sagan had as the Voyager spacecraft was leaving the solar system after visiting Neptune. They turned around the camera and decided to take a picture back at looking at Earth. And so this is everything that we've known, everything that we've loved, even very close at the edge of the solar system on the grand perspective, everything fits into a single picture. It's kind of a powerful image. And when we zoom in, it's more than a pixel to us. It's our home, and it's this lovely planet. And how we build and how we take care of the planet, even as we think about how we step away from it and venture out the universe, is super important.
The way we approach a project like space travel would be in collaboration, we believe. In 1936, our founding partners, Skidmore, Owings, and Merrill, SOM, had exactly that same idea. First, it was Skidmore and Owings, two architects, who were joined by Merrill, an engineer, shortly thereafter. And ever since that, this has been in the DNA of SOM. Skidmore and Owings got their first break at the Century of Progress exhibit in Chicago in the mid-1930s. It was a big fair, and they realized this incredible skyride project that you can see on the screen here. It was used by about 5 million people almost in a time where air travel was not standard. And so this was probably as close as somebody could go before like planes were readily available or space travel was available. So you were in a capsule riding 60 meters up in this little capsule over the water. Next. Ever since then, SOM has expanded obviously globally in the last 8 decades. We have basically followed our clients to all the continents of the world. In the last 80 years, we have executed about 10,000 projects. And this DNA that I spoke about earlier has stayed with us. Skidmore and Owings and Merrill, the engineer and the architect, then Fazlur Khan and Bruce Graham, and then all the other the next generations that came, architects and engineers working together. We believe that this is the best this is the best setup, produces the best architecture, best engineering, but also like we don't just do that. We also have like designers, urban planners on staff. And when you look at our architecture that we produce here, for example, the Willis Tower, formerly the Sears Tower in Chicago, you can see that the architecture derives itself out of the structural engineering and vice versa. This is a bundled tube concept that you can see from Fazlur Khan, a world famous engineer of its time. And this is a great example for how we see a successful project, how we like to work together. Next, please. Another example that kind of shows this working together in collaboration that we at SOM like really love is the Broadgate project, the Exchange House in London, 1990. It is a bridge, but it's also a building. You can see it very clearly, you know, how it spans over this big area, which is basically occupied by train tracks underneath. So again, we architects work together with structural engineers in collaboration. And we believe space travel is another one of these projects where we have to collaborate together in order to have a good outcome. Next, please. Besides project work, we also do a lot of research. We try to stay at the cutting edge of technology, of like production of buildings, additive manufacturing that may be applicable later on the moon is something that we are looking into. And ever since computer technology has made its way into mainstream architecture and structural engineering, we have been right there with it. And we've always used the tools of the time And whether it was like AutoCAD or Revit or Grasshopper nowadays, or and all these different types of tools, platforms, we have utilized them. However, when there was no tool available to us, we would just like develop it ourselves. There's a whole list of tools that were authored by SOM over the years, and make our engineering usually successful. Architecture profits also from this, but a lot of engineering tools, as you can see here, have been developed by SOM.
And so we are taking all of this cultural history of our project, of a way of working, and applying it to designing for habitats in outer space. And particularly this wonderful idea that Jan Werner just described, of taking the inspiration of going to space together is personified in the International Space Station, and then applying it to how we could live in the moon. And instead of going to the moon as adversaries competing, if we all pull our resources together to create a common infrastructure, then everybody can share in it, and we could all go to the moon and explore it and settle it together. And so SOM, in partnership with the European Space Agency and MIT, for the last 2 years, we have been exploring ways of how to give form to this idea of how we would go to the moon together. We have chosen a site. Over the last 20 years, over many missions by different countries, we have accumulated quite a bit of evidence that the most interesting bits of the moon are the two poles. And mainly because the two poles, the way the moon's orbit works, have these permanently shaded regions where the sun never shines or hasn't shone for billions of years. And in these permanently shaded regions, there's very high evidence now from these many missions that there's ice, and most likely water ice and other volatiles that are permanently frozen in a sort of a big cache of reserves. The rest of the moon on the equatorial region, where the sun shines all, most of the time, everything boils off, and so it's bone dry. In fact, if we go on the moon and find concrete, it would be worthwhile to mine it for its water. But on the poles, we believe that the water is stored in vast amounts. And in particular, if we zoom into the South Pole, besides the permanently shaded regions, also very nearby, there's very high points that coincidentally are also exposed to almost permanent sunlight, quite the opposite. And those are really good that you could harvest the solar energy to create electricity. So you have both water, which is both interesting because it provides a resource, but it also is very interesting scientifically because it's locked the history of the solar system for the last 4 billion years. So it's interesting both as a resource and as an object of scientific study. And right next to areas where you have permanent light. And so if you look at it, there's this South Pole, and then there's this giant crater that's called Shackleton Crater. It's about 4 kilometers deep. It's about the length of Manhattan from side to side, so it's pretty big. But on the rims of it, there's these smaller craters that you see here on the left as well, where it would be easier to land and explore. And you have very near to each other both permanently shaded regions and permanently lightly exposed regions. And we have studied the topography very well. There's a lot of good information. So you can build a very detailed map of it. And then we have, after picking a site, we wanted to start imagining how you would build a moon village or a settlement that keeps growing over time. And it's not just a one-off event. And when you set off to create a new urban environment, you have some criteria, right? You have to have safety, which is very important. It's a very harsh environment. And so all of your modules and all of your habitats must be linked together. So if one of them goes off, it doesn't cut off the rest of your settlement from each other. It must be efficient because everything in the beginning, especially, you have to bring from Earth. And as we know, space travel is quite expensive. So you must not lay out your infrastructure in an inefficient way. And it must be easily expandable, because our idea and the goal here is to keep growing in the future. And so we looked at several precedents of how humans have settled on Earth before. Many places you have grid plans, both in South America and all the South American cities that were laid out based on the law of the Indies, and then the Jeffersonian grid that dominates the American Midwest, that started expanding from the Appalachian Mountains on. So these are provide a lot of redundancy and safety and expandability, but they also create, if you want to have habitats that are connected together, a lot of closed spaces where you can't access it. We also looked at other sort of utopian urban planning ideas, the radial garden city from the early industrial revolution, or the ideal Renaissance cities from Italy. But we settled on this idea of the linear city, first made popular by the Spanish architect Arturo Soria, and then given most famous form by Le Corbusier. This idea of how you would use the modern industrial society and lay it out in an efficient way. And so you have these bands of development where you have the infrastructure and the industry interspersed with the habitats. And so if you take this idea, you could have a band of habitats. Here in this master plan, the rim of the crater is east, left to right, and the big crater is on the south. So on the perimeter of the crater, you could lay out all of your habitats, and they could grow in both directions. And then next to them, you could have all the infrastructure that you need, the solar panels, the resource extraction that grow with the habitat. And finally, you can have sort of an activities band. You can imagine the different players coming to the Moon Village. Say, for example, you have a government agency that wants to set up an exploration and go roving around to explore the region. They need the staging ground. And right next to them could be a tourist company that wants to bring tourists to the moon, and they could have all the playgrounds there where you would come in and experience fun, new ways to, and lunar Olympic Games or things like that. And you can see the precedent like this on Earth. This is the Scott Amundsen South Polar Station at the very south pole of the Earth. And you could see the linear new development. There's the original dome from the 50s, then a new settlement, and then all of the infrastructure in building the settlement is all laid out very neatly. But besides these practical reasons of how you lay it out, every human community also needs a symbol. So, you can end up with a mess like this. This is another station down in Antarctica. This is McMurdo, which is the biggest settlement on the edge of Antarctica. And here, everything is laid out haphazardly and looks like a big sort of a mess. It doesn't really have a sense of place and identity. And if you look at all of our most famous cities, there's always some kind of a urban green space that gives an identity. You can recognize it immediately and gives a pride to the residents. There's the Central Park in New York, or Tower Bridge in London, or the Eiffel Tower and Champ de Mars in Paris. And so we were thinking of how we could create this on the moon. And we had this idea that we probably want to have a piece of undisturbed moon left over, so that as you move around and lay tracks and sort of make a human mess, there's always a piece of the pristine moon settled as a sort of a moon park. And the best place of it is to put it in the direction of the Earth. And because of the moon's rotation, Earth is always kind of sitting in one spot on the horizon. It never moves, and it's always there in one location. And in our settlement, it's to the right over here. And so we had this idea that if we keep this piece of pristine moon, there would be this poetry that everybody from each habitat would look on the untouched moon and then see behind it the beautiful Earth spinning around in the sky. to give it a sense of identity and beauty in addition to the thing. And so if you're back in the settlement a little bit, going down into the crater, for example, or something like that, you would see your settlement with the earth behind it always in this beautiful image. And so this is sort of our idea of the master plan. We started laying out our habitats and how you could aggregate them together in this linear fashion. This is a higher up rendering from here. In this case, the crater wall is on the upper part, and you see the band of habitats growing, and then the solar panels and other infrastructure that's holding the life support.
The differences that we as engineers and architects face on the Earth versus the Moon couldn't be starker. The Earth is more than 3.5 times bigger than the Moon. The average temperatures on the Moon significantly colder and significantly hotter. As you can see, it dips down to minus 240 degrees Celsius and goes up to 127 degrees Celsius at its peak. So the range that we have to accommodate with our structures is significantly bigger than on Earth. The force of gravity is obviously much, much less, about 1/6. And interestingly, also the lunar day is significantly longer, as we all know, about like 30 days. So that is also an important criteria when it comes to like the location, finding a good site, as Georgi already talked about, for harvesting the solar energy with PV cells. In terms of what the structures will have to withstand, on Earth, typically we have gravity. On the Moon, gravity is not the issue. On the Moon, it is actually creating pressure for human life. To withstand these forces, the systems that we have to construct on the Moon will have to be capable of withstanding probably 10 times forces that we have to have them sustain on Earth. And so that is a significant difference that especially structural engineers have to keep in mind when they design on the Moon. We also have radiation on the Moon that we have to be very, very cognizant of. There's a low-level radiation that is constant, but there's also so-called solar flares that happen once in a while and can be predicted and can be, like the weather, can be foreseen. And astronauts will have to take cover during these events. And so our structures also have to serve as shelters to protect the astronauts from from radiation. Traditionally, spaceships were constructed as gigantic fuel assemblies with a little bit of a payload on top. You can see the three types of spaceships we've seen in the past: the Vostok, the Mercury, and the Apollo, where there's a tiny little last stage at the top of the rocket ship that actually made it into orbit. Skylab also was transported into the components of Skylab was also transported into space at the tip of a rocket ship. And this is a traditional concept of like taking rigid components into space that do not change their shape. The outer shape conforms to aerodynamic and structural requirements, and there's no flexibility. This kind of old school concept has been kind of changed or there has been an evolution in the 1990s to be a little bit more flexible. NASA developed a system where you had a rigid core that would be that would fit beautifully into spaceship compartments, but there was also an additional flexible membrane that could be expanding once the components were in space. So this was like a way to be more efficient and create more space while not having to build bigger rocket ships. And to summarize this, there's different classes of systems that the scientists categorize. Number one is the class with the rigid outer shell that doesn't expand. Class two is the latest development from the 1990s, where we have this flexible outer components that can significantly change the shape of the module and give you more space. And class 3 is the future, probably, where we use in situ material on the moon, maybe, to build structures with material on the moon to be efficient, so we don't have to take building materials up to space, which obviously is very uneconomic. So understanding all of these considerations, we synthesized and developed a scheme for the individual module. So we developed the architecture of this module. First things first, the module had to be shipped somehow to the moon. So it had to fit into the compartment of the carrier. And we embraced the class 2 configuration we just talked about, where we have a rigid core that can be expanded once the module is on site. You can see in the foreground the deflated system here module with a diameter of about 8 meters. And in the background, you can see the inflated module, which pretty much like doubles the volume of this module. Next. You can see here the inflated module in situ on the moon, and very nicely on the right side, you can see the rigid kind of triangular shaped framing in the darker color rendered here, and you can see the pillows, the 3 pillows that get like inflated once on the moon. Architectural floor plans here. The module has 4 levels. On the left, you can see the first level where you basically have connections to other modules as illustrated here on the top right, or you can step down to the surface of the moon. Use of this, this first floor is basically for like as an entry vestibule, a suit maintenance, a workshop. You could say like it's the mudroom of this module. Up on the second floor, we find the lab and research area, and you make your way up in the center, which is the which has a ladder, so you can kind of guide your way up. Next. On the third floor, we have the sleeping quarters of the crew, where they can, well, sleep and live and entertain themselves. And then up on the very top level, the 4th floor, we have an experimental greenhouse where the crew is trying to learn, hopefully, how to grow plants while being on the moon. So of course, on the moon or in a module like this, every inch matters, every ounce matters. So the study of the human body is particularly important. And so taking all this into consideration, all these, the reaches of the human body and the dimensions that the human body typically has, we designed the system, we programmed it, and you can see nicely how it's broken down into the circulation in the center, which is kind of a new idea here, to have a rigid frame around it, but circulation in the center. We see the structures here, the different 4 levels, storage compartments in the walls. And altogether, the system has about like a net habitable space of 100 square meter, which is a nice 2-bedroom apartment in New York City. Next, some visualizations of what the 2nd floor could look like. Circulation, as I mentioned, in the center. Next, we go up to the 3rd floor. You can see how the living quarters may be with individual sleeping alcoves here, niches. And so we looked at the architecture of this module. Now we would like to take a closer look of how the architecture could be, with what kind of components the architecture could be built.
And so zooming in even further into the details, we took already the research that was done for TransHab in the 90s of the different layers that the expandable shell needs to have in order to survive, to function properly. So there's typically a layer of Kevlar woven together like a basket that holds the pressure. It's the main structural layer. And then there's several layers of insulation. On the very outside, there's a micrometeorite protection against particles that might hit from outer space. And then on the inside, there's several bladders that actually hold the atmosphere. And finally, on the very inside is the finish that the astronauts would come in touch with and experience. On the Transcab, these are images back from the 90s, they developed it quite a bit, and especially different strategies for folding this very complicated multi-layered shell into the rocket and how it would expand. This is actually a full scale. You can see the scale of this, the individual people, a large vacuum chamber down in Houston where they could test it in vacuum and how it would inflate and behave in vacuum. This technology has been moved forward in the last few years by several private companies. There's actually a demonstration of this technology that's up attached to the International Space Station right now, this module by Bigelow Aerospace. And then other companies like Sierra Nevada have built full-scale mock-ups of how this inflatable structure could be. And you can all see both the original Transcab and these two are quite symmetrical and simple in shape, and yet it's very complicated how the weave of the structural layer could happen. And it's a really difficult material to model. It's not like a solid piece of steel or concrete that you fairly know how it behaves and you can and make predictions and model. It's very non-linear because the molecules themselves are stretchy, and then they're woven into fibers and yarns that then go into the webbing. In each layer, there's give and take, and the mechanical behavior of the material is very difficult. And so we're looking at different ways that we could weave the mesh together to create this sort of rather complicated surface that we're imagining out of the three-partite shell for our module. We're also testing it with finite element structural analysis to make sure that we're modeling the shape of the inflated shell correctly, and that all of the forces can be accommodated with the thin Kevlar strips. In addition to studying the shell in detail, we're also studying how the floors and all the rigid structures would unfold, because they have to be packed closely during launch and transfer. And once the module makes it to the moon, we're studying how we could cantilever and fold out in 3 dimensions the floors. And then in addition to the floors, all of the rigid furnishings, the crew quarters, the lab equipment, everything to be expanded and moved out into its final configuration along the open shell, freeing up the middle for the circulation and habitable volume. And so again, here you see the final configuration of the shell. The very important windows that we talked about, so you could see and experience the outside, are built into the rigid frame, where it's a lot easier to introduce openings and attachments rather than into the woven shell that has to be inflated and moving. We're reserving that only for the connections down at ground level. And then we're imagining how you could start multiplying these. In the beginning, the very first one obviously has to have everything that you need to, and we've designed it in such a way that it has both the working and the living example. As you start adding more and more, you could, just like on Earth, you could start imagining that each one would start taking on a specific function and specializing. So you could have one module that's the habitat, another module that's the working environments and labs and the workshops, another module that could be a hotel for temporary visitors, another module could be storage. Additionally, a very important activity on the moon would be studying how we could use the resources there. And here we could experiment with 3D printing, for example, a hardened shell made out of the local materials and the regolith on the moon in order to protect a portion of it for radiation events like solar flares and things like that. And then later on, we can imagine as the moon village is growing, another interesting activity would be to try to learn how to build and construct full habitats on the surface of the moon out of the local resources. And all of the experience that we'd have gotten could be, we're very excited about the cool new architecture that would come out as humans live and learn how to live on the moon. And so we've been very excited to be working on this project. We have contributed our expertise in urban design and architecture and enclosure design. And we've been very fortunate to collaborate with the real experts on space technologies from the European Space Agency and MIT, who have sort of explained all of the technologies to us and given us feedback to make sure that everything that we're showing here has a level of realism and could be really useful in designing the final way in which we'll live on the moon.
We talked about collaboration earlier, and we believe that this is really the name of the game on this project here, that a lot of disciplines will work together, architects, engineers, urban planners, designers, you name it, and together with other countries, we can work so we can all make it to the moon. And I think events like this are very helpful to bring people together and pull this off. It's quite an adventure, and we hope that you enjoyed this talk, and we are really looking forward to the next presenter. Thank you.